start yelling profanities. Just kidding.
Okay, so
Hello,
let's do a quick recap of what we talked about yesterday. I joked earlier, like, welcome to Gambling 101. That's kind of a big place where probability goes. So yesterday, okay, most of you guys were here yesterday except for you two, right?
Yes.
Okay, so quick recap of what we did yesterday. I bought $20 worth of lotto scratchers. And I went online and I found the stats on the theoretical probability of what should happen. And it says that we were supposed to win 1 out of every 4.75. Which, when we extrapolated that, I played 20 tickets. We were supposed to win on 5 tickets. And if you guys remember yesterday, we actually won on exactly 5 tickets. The downside is that although the odds were winning 1 in 5, and we won basically 1 in 5, 1 in 4 technically, I didn't make my money back, right? I invested $20 in lotto scratchers, and I believe it was 3 $1 wins, and you scratched off a $2 win. And that was all we got. So, I mean, lesson learned here is that we exactly met the odds that we were expected to, but the system is rigged, right? You're not supposed to come out ahead. I invested $20, and I ended up losing $15. Does that make sense? No, I mean, I had $5 back, so 20 minus 5, 15. Does that make sense? So yesterday I was basically introducing, or maybe reintroducing, some words that you've probably heard before. So that was on this slide here. The idea of what does an experiment verify when you actually test it, and what theoretically should happen, right? And there's so many places where probability and odds and this sort of stuff come up. I mean, sports is a great one, right? If you have to choose which player, we did an example here of hockey players. Here are some stats on some of the best shootout players. If you have to pick your best shootout player, do some stats, figure out who's got the best percentage, right? Don't send out the guy who's 1 for 94 because he sucks, right? Pick the guy who is 33 for 72 because he's probably a little bit better. That makes sense? So sports is great for this. Actually, sidebar, anybody ever seen the movie Moneyball? Brad Pitt, Oakland Athletics? You guys have? Right? Oakland Athletics, they introduced a new concept to baseball called sabermetrics. You guys don't need to know this stuff, but basically the concept was they started building their baseball team based on stats, and they were trying to figure out who statistically was the best player by doing basically some number crunching. And it worked out really well for Oakland because they were a team that had a very small budget. They couldn't afford to pay like the New York Yankees and the Boston Red Sox could, so they had to try to find cheap players, but they had to try to find cheap players that were still going to be good baseball players. So yeah, they used statistics to try to find them, basically. So, gambling obviously really fits with this too. So, I mean, I'll show you guys some poker examples over the course of the unit. This example right here was basically Texas Hold'em. What are your chances of winning? So, and then we just did we just did lots of examples. So I think by the time we finished, where did you say we finished, Lisa? Is it this one here?
Yeah.
Okay, cool. So why don't we pick it up here? Why don't we finish this set of notes here? And we'll take a break, and then I'll talk about mutually exclusive events. So one of the things I didn't mention as I was recapping is the basic formula for probability. I don't think it's on any formula sheet, but it works like this. The probability of some sort of thing happening is equal to the number of ways in which it happens over the number of ways total. You may see this notation written like this. Capital P means probability, and N just means the number of ways that it occurs. That make sense? So let's try this example. You've got a committee. It's got a pres, a vice president, a treasurer, and a secretary. We're going to randomly draw names. What is the probability that Jane will be president? Doris is also on the committee, and there's 10 people total. So I'm going to start with the bottom of the fraction. How many total ways can you make this committee? How many people are applying for the committee? How many jobs are there? Does that make sense what I just did? The total number of committees would be 10 choose 4. There's 10 people applying, and 4 of them, there's 4 jobs out there. It's choose because, actually, I screwed up. Why is it not choose?
Because if it's random, it's The
Not
order
because of that.
matters.
The order matters. If it was just a committee in general, it would be choose, but there's a president, a vice president. Since there's like titles to these jobs, I screwed that up. It's not choose, it's actually pick. Because of the fact that there's actually like specific job titles. Does that make sense? If it was just on the team or off the team, that's choose. But if it's on the team and you're captain, and it's on the team and you're the assistant captain, and you guys are off the team, if we now have a ranking system, then it's pick. Okay, now let's talk about the top of the fraction. We need to try to find the ways in which Jane is president, Doris is on the committee, and then there's two other random people. Does that make sense? So I might try it something like this. I'm going to put like 4 different blanks here. Here is the president. Who has to be president? How many choices do I have then? I guess I just have one choice. Well, now I've got some issues here. It says that Doris has to be on the committee. So I guess there's 3 ways of approaching this. Doris could be vice president. Doris could be treasurer, keyword here, or Doris could be secretary. That makes sense? So I'm actually, maybe for the sake of doing this, I'm going to write this over here a little bit. We could have the committee where Jane is president, Doris is vice president. We could have the committee where Jane is president, Doris is treasurer, and we could have the committee where Jane is president and Doris is secretary. You see how I just did that? This column here is president. This column here is vice president. This one here is treasurer, and this one is secretary. So it could be Jane Pres, Doris vice president. It could be Jane Pres, Doris treasurer. It could be Jane Pres, Doris secretary. That makes sense? But either way, these are the people that have to be in those locations, right? How many people are left then to be treasurer and secretary? Hang on a sec. There's 10 people applying, right?
8.
So Doris is out, Jane is out, so now there's 8 people left who could be treasurer, and 7 for secretary. And doesn't that same sort of logic apply here? Here, if Doris and Jane are locked into these positions, then there's 8 who could be vice president, 7 who could be secretary. That makes sense? What should I do with this little mess of work I have right here? I need to add and subtract these numbers, or add and multiply these numbers. Where do the multiply signs go? Where do the add signs go?
Unless you multiply the dash one, like
Okay.
1, 1, 8, 7, and then after that you get your total and just add the total.
That's correct, yeah.
Wouldn't it be the same answer every single time though?
It is, because this guy right here is going to be 56. This one's going to be 56. And this one's going to be 56. My question then was, what do I do with the 56s? And Dakota's right, you add them. Because, let's talk this through here. Here's a committee where you have to have Jane as president, and Doris as vice president, and you need 2 other random people.
You don't do the exclamation mark?
Well, if you do the exclamation mark, though, it means all the rest of the people also get to be on the committee. But they don't, right? They don't make the cut this time around.
So how do you know to add those?
Okay, so this is one way you can have the committee. You could have Jane and Doris as president, vice pres. Or it could be Jane as pres and Doris as treasurer. Or another possibility is Jane as pres and Doris as secretary. Does that make sense? Because I'm using the word or, this is one way of making committee. This is another way of making committee. Or this is the third way of making the committee. All of them are 56, by the way. So maybe on the top of this fraction right here, I should just say this is all going to be 56 plus 56 plus 56. Does that make sense? Okay, let's find a calculator, I guess. Is that the top of the fraction?
Yeah,
Right. And then bottom of the fraction?
I agree.
Okay.
You know what?
Okay, so 56 times 3 is 168.
I just did it all together. I got 0.03.
Sure, why don't we just do
Yeah,
that?
I got it too.
What'd you get?
0.03 repeating.
Okay, cool.
No, 0.03.
Oh, 0 through repeating. Ah, thank you. So let's talk that through one more time. Bottom of the fraction, the total number of ways. There's 10 people applying for 4 jobs. But these jobs are different, so that's why it's picked. On the top of the fraction is kind of a challenge. There's 3 ways of making a committee. You can make the committee where it's pres and vice pres. You can make the committee where it's pres and treasurer. You can make a committee where it's pres and secretary. Regardless of that, when those people are out of the running, there's 8 and 7 people left for the other 2 jobs. So 8 and 7, here stagger the 8 and 7, here's the 8 and 7. Long story short, there were 56 ways of making this committee, or you can make the committee this way, or you can make the committee this way. So that's what goes on the top. I've said this a lot, so I'll say it again. Your struggle is not going to be in doing adding, subtracting, multiplying, dividing. Does that make sense? Like, that's not the hard part. The hard part is interpreting where they go, right? So here we need to multiply. Here we need to add. Here we need to divide. Actually, I said this yesterday. The best way for you guys to do well in this unit, you gotta do that little triangle I was showing you there, where it's like, do I have it nearby here? I do. I'm going to show you some stuff. You got to practice it, and you have to let me give you feedback. Because if you just watch, you'll probably go, yeah, okay, that makes sense. Or you'll be frustrated because you'll be like, I'll never get this on my own. We've had that conversation before, right? Which is why, like, if you haven't done the quiz, if you haven't done the assignments, I want you to do them, not because I need you to get a grade on them, but because I want to be able to give you feedback so you get better. Does that make sense? Because it's a weird sort of math unit. It's not like algebra where you can just practice a lot of it, right? You have to try, fail, try again. Okay, did that make sense? Let's try another one. There's a banquet, and there's a table with adults, another table with kids, and another table with seniors, and they're going to give away some prizes.
Sorry, there's a bunch of dogs out there.
I'm distracting you. Okay, I'll even draw a picture here. So you've got a table here. There's 6 adults, A, B, C, D, E, F, G. These are the adults. Then there's a table with 4 kids, F, G, H, I, J, kids. Then there's 5 seniors, G, H, I, J, K, L, M, N, O, seniors. So first question, how many people are sitting at the banquet in total? How many total do we have? 15, yeah, okay. It says that there's 3 door prizes. Well, that means that there's 15 people, and 3 of them are getting a prize. Does that make sense? So if I wanted to write it out like this, the probability of something happening means it's the number of ways that our special event occurs over the total number of ways. The bottom of the fraction basically says there's 15 people. 3 of them are getting a prize. So, first challenge then, pick or choose. Based on the info we have, does it appear that the prizes are different and therefore there's a big difference between them? Or does it just seem that, based on the info we have, that you either get a prize or you don't? I would go with what you suggested there. I don't have any info that seems to indicate at this point that like one of the prizes is $1 million, the next one's a car, and the last one's a paperclip. Does that make sense? Because if that was the case, then I'd go with pick. Here it just looks like you either get one or you don't. So that's choose. Now the question is, what's the probability that all the prizes go to people in the same age range? Well, this is another and scenario. We could give all the prizes to the adults. Or we could give all the prizes to the kids. Or we could give all the prizes to the seniors. Does that make sense? So, how many adults are there? Well, there's 6 of them. Well, of those 6 adults, we need to choose 3 of them to win. Or, what if we don't let the adults win? What if we let the kids win? Well, how many kids are there?
4, 2, 3.
Yeah. Or there's 4 kids. We could let 3 of them win. Or there's 5 seniors. We could let 3 of them win. See how that works? It's a bit of multiply and add and divide all in one question. 6 adults, let 3 of them win. Or 4 kids, let 3 of them win. Or 5 seniors, let 3 of them win. That's the stipulation where 3 people win in the same table. On the bottom, we don't care about any restrictions at all. So we just say on the bottom, there's 15 people, 3 of them win. Anybody get an answer?
Well, I messed up.
All right. as the number, like 24 point something. Okay, so here's a good talking point. You cannot have a number that is greater than 1 or less than 0.
I got .074.
Yeah, you should have a decimal number. So my guess here is that you need to make sure you put the top of this all in brackets. Did you guys not do that?
I did the bottom in brackets.
Okay, I would say the top and the bottom in brackets then.
I just did the top like separately.
And then the bottom?
Together,
Okay,
then
that'll work, because I think what you did here is your calculator thought that you wanted to do this number, add this number, and then this number right here, you're dividing it only from the last number, as opposed to dividing all of it together. So that's why I had that really big slide a ways back. If you guys remember the slide right here. Most important thing ever. Where is it? You should never be less than 0. You should never be greater than 1. So if you get something like you guys got 24, that's not possible. So it means you mistyped something.
do we have an answer to that? It's .075 rounded up.
Anybody else get that one?
It's like 0.074.
Here, let me try it too. I want to just double
I
check.
got what you got. Cool. Yeah, I got
Plus
0.
5 math, choose 3. So here's what I'll just do. I got 34 on the top,
Yeah, so I got
and then 15, choose 3, 455. And then 34 out of 455. Yeah, .074725.
Yeah.
Cool.
I just rounded up to .075.
Did that make sense?
Yeah.
Okay. Again, the struggle is going to be, I can show you it, right? And you listen and you go, yeah, that made sense. The struggle is, can you do it by yourself? Because I was actually trying to help a couple of you guys write a quiz. And I can't help you write quizzes this time around. Because if I explain it to you, there's nothing else other than the explanation. You know what I mean? Like the work, the actual typing numbers in your calculator, that's got to be a given, I imagine, right? If I explain to you, well, you should use pick over choose, I've done the question. I've spoiled the joke. So, okay, scenario here. You're about to go play a game to win a big car. They give you 6 tiles all face down, and you have to arrange them all. If you arrange them in such a way that they spell the word winner, you get the car. Now, if you spell it like this, W-I-N-N-R-E, you don't win the car. So you have to put the tiles in the right way. Does that make sense? So let's see if we can figure this out. The generic formula is the probability of something occurring is the number of ways in which you can win over the total number of ways that you can do things. Okay, how many tiles are there? 6. Do we need to use all of the tiles? Does the order in which you place the tiles matter?
Yes.
So pick or choose. Cool. Okay. So there's the bottom of the fraction. There's 6 tiles. We need all 6 of them to be used, and order seems to matter. That's the number of total ways you can arrange things. By the way, 6 pick 6 is just 6 factorial. So if you'd have written it as 6 factorial, that also works, by the way. In a way, you're being asked pick one of 6 tiles. Okay, well now pick one of 5 tiles. Now pick one of 4. The harder question now is, how many different ways can you spell the word winner?
1, 2.
2. Why is it 2?
Because the ends can switch.
Yeah. See, there's the word winner, W-I-N-N-E-R, but do you guys see how there's 2 ends there? You could flip those 2 ends around. So there's actually 2 ways of winning. Does that make sense? Or here's another way of approaching it, just with the word winner. Okay, the first letter has to be a W, right? Well, that means that you've only got one way of doing that. You have to use the W. The next letter has to be an I. Well, there's only one I, so you have to use an I. The next letter has to be an N. How many N's do you have? 2 of them. The next letter has to be an N. Well, there's only one N left because you used one of them. The next letter has to be an E. There's only one E out there. And the next letter has to be an R. And I've been saying the word and in between all of these. So how many ways is there to spell the word winner? There's 2 ways. So your odds are 2 out of 6. Pick 6. Whatever that is. 2 divided by 6 factorial, or 6 pick 6, whichever one you like. Yeah.
0.002777.
Yeah, so that's not even 1%, right? Because if you did times by 100 to make it a percentage sign, it would be 0.27%. So, are you going to win the car? Well, you could. Right? These are your expected odds, right? Theoretically, that's the chances. That being said, this is how lotteries suck you in, right? We talked about this yesterday. Someone eventually wins the car, right? And they try to, they make a big deal. It's on the news. They put their pictures on Facebook. They give them a big novelty check, right? And they make you think, look, that guy over there won. You can too. But you know what I mean? Like, the odds of that happening are, you probably heard this before, like, the odds are actually better that you get hit by lightning than that you'll win the lottery. You ever heard that before?
No.
Yeah, like, the odds are better that you get hit by lightning. So think about how rare that is. Okay, another example. And then, like I said, we'll take a break partway here. You've got 18 bikes in a room, and the way they're arranging these bikes is a 3x6 grid. I hope that makes sense here. You've got 1, 2, 3, 4, 5, 6. Then another row of 1, 2, 3, 4, 5, 6. And a third row of 1, 2, 3, 4, 5, 6. To keep this one simple, I've given everybody the name that starts with a letter starting in the beginning of the alphabet. So Alice, Allison, Brett, Carol, Doug, Erica, and Franco are each getting a bike. We want to figure out what's the probability that all 6 friends somehow end up in the same row. Okay, well, let's use that same formula.
What if you 18 bikes?
Well, that's going to be part of it. Like, we're going to say there's 18 bikes and we need some of them used, but let's write the formula out, though, again. So, we need to know the number of ways in which they're all in the same row over the number of ways total you can arrange them. How many ways can you arrange these people?
6 ways.
Okay, hang on one sec here. There's 6 of them. I should point out, by the way, the rest of the bikes are getting filled. Maybe I didn't say that in this question here, but we're actually going to have all of the bikes be filled. So let's say that I asked for someone to go to this bike right here. How many people could go there? 18.
Oh.
Then how many people could go to this bike here? 17.
Oh.
Then 16, then 15, then 14, and then back down here, the last person in the room gets the last bike. Good. So you can either say that the total number of ways is either 18 factorial, or another way of approaching it, by the way, is say, well, there's 18 bikes, and we need to pick all 18 of them to get used. Does that make sense so far? So all 18 bikes, if I didn't make it clear in the question here, we're using all the bikes. Okay. Now the question is, though, how many of those arrangements involve all 6 of these friends somehow being side by side? Well, this is another or scenario. They could all be side by side in the first row, or they could all be side by side in the second row. Does that make sense? Or they could be all side by side in the third row. Does that make sense? So let's talk about those possibilities one at a time here. Let's say they're all in the first row. You've got 6 friends, right? Well, you could have 6 people who go in this one here, and then 5 of the friends could go there, and 4 of the friends could go there, and 3 of the friends could go there, and 2 of the friends could go there, and 1 of the friends could go there.
So you go 6 factorial plus 6 factorial plus 6 factorial.
Not quite, though. We're almost, you're right, but you're not quite there, though. Okay? Those are the 6 friends all in the front row. However, everybody else still needs a bike. So how many other people are left? 12. So there's 12 to go on this bike, 11 to go on this bike. Does that make sense? 10 to go on this bike, 9 to go on this bike, 8 to go on this bike, until eventually you get down to 1 person on the last bike. So in this particular orientation where the friends are all in the front row, there's 6 factorial ways of arranging the friends, and there's 12 factorial ways of arranging everybody else. That's what you were missing, eh? You're missing the everybody else factorial. Now, that is where we arrange them where the friends are all in the front row. But what if the friends are in the second row? Isn't it the same thing? Mm-hmm. Right? So then we'd say, well, or these are the friends in their row, and here's everybody else in the other rows, and here's the friends in the back row, and everybody else in the other rows. Does that make sense? So one more time from the top. Here's the 6 friends in the front row. 6 choices, 5, 4, 3, 2. Franco's got to stand there. He's lost. But what Lisa missed is you got to times by the 12 factorial because everybody else still needs a bike. Other possibility is, what if the friends were all in the middle row? Well, then it's a 6 factorial for the middle row, and then it's 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 around them. Or, same logic, the friends are all in the back row. So 6, 5, 4, 3, 2, 1, everybody else here. Does that make sense? So maybe a fast way of doing it is it's 6 factorial times 12 factorial times 3. And on the bottom, there's 18 factorial because on the bottom, there's 18 people, they're just all taking a bike.
I got like 1.6 something times 10 to the negative 4.
Okay, so let's talk about that answer. You got 1 point, give me 2 digits after this.
Well, after dividing it and everything, I got 1.62 times 10 to the negative 4.
Okay. Ooh, not 14, just 4. 1.67?
6.
2 times 10 to the negative 4. Okay, so what this means is as a decimal number, it is 0.000162. Does that make sense? This is taking the decimal place and moving it over 1, 2, 3, 4 times. Is it likely that by random chance all 6 friends end up in the same row?
No.
Probably not. You can end up with, say, 5 of them in the same row, but that doesn't count. You can end up with 3 of them in the same row, that still wouldn't count, right? So like the odds of them being all in the same row, that's pretty odd. Follow-up question. What if Allison and Franco have to be at the ends? They're just like Sheldon Cooper off of Big Bang Theory. They're a little bit OCD about where they sit. And they have to be at the ends. Yeah.
Wouldn't that be 4?
Okay, let's draw it out here. So let me draw out another diagram here.
Maybe I'm wrong. Would it be 2 factorial and 4 factorial because
You're right. There is a 2 and a 4 factorial hidden in there.
they can switch spots?
That's it. Okay, so let's try diagramming this out. Would you guys agree that the bottom of the fraction is still 18 factorial? Because there's still that many ways for everybody to randomly take a bike.
Yes.
Okay, so let's do the same thing we just did right here. Let's say that they're all in the front row. This has to be Allison or Franco. Well, that means I've got 2 people who could be here. Well, if this is Allison, then that means that one's Franco. So that's kind of your 2 factorial, because you can have these 2 people wherever they want. The remaining 4 bikes in the middle for the other 4 friends is like a 4 factorial.
And
So
then you do 12 still.
But then you still have the 12. So what you have is a 2 factorial for Allison and Franco flipping their spots. You have a 4 factorial for the 4 friends flipping their spots. You have a 12 factorial because the other 12 people can go wherever the heck they like. Times by 3, because this can happen in the front row, the middle row, or the back row. For like the 20th time I've said this, you're just multiplying numbers, you're just adding numbers. That's your struggle. If you can interpret, if you've got good deducing skills, what did you say yesterday again? Deciphering?
Yeah.
If you can decipher the question, that's your battle. No. So, I think I've said before, it's kind of like social studies and interpreting sources. That's what this is like. You're given a source, you got to interpret what's happening. So, 2 factorial times. Oh, you already have it?
Well, I already converted it from like it was
Sure.
0.0000117.
Sure.
After that.
The odds, comparatively, this is the probability of them all being in the same row. This is the probability of them all being in the same row. And, oh, by the way, Sheldon's a little bit OCD and has to sit at the edge. You know what I mean? Like, the probability of adding an extra restriction makes it even less likely. That make sense? Cool. Okay, let's do one more example. This is the last one, right?
Yeah.
And then we'll take a break. Poker time. Like I said, I'm going to teach you to gamble. So, are you guys somewhat-ish aware, learning, I guess, about the different type of poker hands that are out there? Like, for example, you get 5 cards. If you have 5 in a suit in a row, at the top of the deck, it's a straight flush. 5 in a suit in a row is just a straight flush. If you have 5 in a row, no suits, it's a straight. If you have 5 of a suit, it's a flush. Anyways, we're going to figure out the probability of you getting these hands. So, the probability of getting 3 of a kind would be the number of ways that you can get 3 of a kind over the total. Let's do the total first. How many cards are in a deck? 52. How many cards do you need to have in your hand?
5.
A five card hand. Does the order in which you're given the cards, does it matter? Like if you arrange your card Ace, King, Queen, Jack, 10, or if you arrange it 10, Ace, Queen, whatever, you know what I mean? Does that matter? Choose or pick them?
Choose.
Choose is right, yeah. That's your first interpretation. It doesn't really matter which order you put these cards. Now the question is, how many ways are there to get 3 of a kind? Okay, so let's talk first. How many suits are there?
4.
Okay, and how many different cards in each suit?
13.
Okay, so there's 13 different ways of getting 3 of a kind, in a way. You could have 3 of a kind aces, 3 of a kind 2s, 3 of a kind 3s, 3 of a kind 4s. Does that make sense? So there are 13 different ways to get 3 of a kind. But we're not done yet, though. Because when you want to get 3 of a kind, there's actually 4 of that type in the deck. And of those 4, you need 3 of them. So there are 13 ways to say there's 4 aces. I want 3 of them. Let me show that one more time. There are 13 suits, so there's 13 tries at this. There are 4 aces in the deck, you need 3. Or there are 4 2s in the deck, you need 3. Or there are 4 3s in the deck, you need 3. Does that make sense? That's why there's the 13 here, because there's 13 kind of chances at it. When I did the scratch cards yesterday, sometimes they try to make it feel like you have more of a chance of winning the scratch cards by making each game kind of be a unique, different one, where you scratch the first round. Oh, I didn't win that one. Okay, well, here's the next one. Does that make sense? It's kind of the same thing here. You could get aces or 2s or 3s or 4s. But we're not done yet, though. This is kind of like the bike question. We've now found the people on the bikes that we care about, but there's still other people. Right? When you get your 3 of a kind, that's what we have right here. We now have our 3 jacks. But we need other cards still.
So wouldn't it just be like 52 minus 13?
Well, so that's the next step here is how many cards are left in the deck? You now have 3 cards. You've taken your 3. How many cards are left?
49.
Okay, so 49. Here's the problem, though. The 49 still includes the other 3, though. Does that make sense? Like if you have 3 of the 3s, there's actually 48 cards left. Because if you accidentally picked up that last of the type, you'd actually have 4 of a kind. And we just want 3 of a kind. So I would say there are 48 cards left that are not your, whatever your 3 of a kind is, right?
I think the 48 choose.
And we need 2 of them. So this is actually what professional gamblers are able to do very well, very quickly in their heads. They're able to figure out what's the probability of me winning. There are 13 suits in the deck, and I need 4 choose 3 of those particular, so there's 13 types of cards in the deck, and I need 3 out of 4 of that type. But I also need 2 other cards, and those 2 other cards can be of any remaining 48. Anybody have the probability?
0.02256.
0.02256. Yeah. So the odds of getting 3 of a kind? Yeah, not that good. I mean, still happens, right? That makes sense? Okay, next one. So I'm just going to erase just little bits of this here. I'm going to leave the bottom of the fraction, because that's not changing, right? You're still getting 52 cards, and you want 5 of them. Now I want to talk about a flush.
So it'd still be on the bottom 52 choose 5.
So yeah, the bottom's still 52 choose 5, because you're still getting 5 cards, and there's 52. But now we want to specifically talk about how many ways there is to get a flush. So like the number of ways to get a flush. So again, how many suits are there? So you have 4 shots at it. You can get a flush in spades, or a flush in diamonds, or a flush in clubs, or a flush in hearts. That makes sense? So you've got 4 ways of that happening. How many cards are in a suit? How many do you need in your hand? You need all 5. There are 13 cards in hearts. You need all 5 of your cards to be hearts. But I'm timesing it by 4 because it doesn't just have to be hearts. It could be hearts or diamonds or clubs or spades. And I've put up 4 fingers, so that's why I'm timesing it by 4. That makes sense? So 4 times 13 choose 5 divided by 52.
That's it?
That one's actually fairly simple, isn't it? Well, I mean, not simple in terms of solving it, but simple in terms of what you have to do. I got 0.00198. Anybody else try it?
0.00198.
Yeah,
That's what I got.
that's what you got too? Okay. If you know much about poker, this is why a flush is more valuable than 3 of a kind, because the probability of getting a flush is actually pretty low. Does that make sense? Okay, last one, then break time. Full House. Not the TV show. Fuller House. Who's binge watched all of Fuller House so far?
My sister has.
You watched them all? And Melissa and I watched them. Okay, so the bottom of the fraction is still 52, choose 5. Does that make sense? There's 52 cards, you need 5 of them. That's how many total possibilities we have. But now we got to try to figure out the way to get that full house. A full house involves a 2 of a kind and a 3 of a kind. Okay, so let's talk about the 2 of a kind first. Well, there's 4 cards in a type, and we need 2 of them. Does that make sense? And you're also going to need the 3 of a kind. Well, pick a different suit. There'd be 4 cards in that grouping, and you'd need 3 of them. But here's the issue. You could have aces and kings. You could have aces and queens. You could have aces and 7s. You could have 6s and 5s. Does that make sense? If you know the poker lingo, you might say like 6s full of 5s, 8s full of 3s. Right? 8s full of 3s means 3 8s and 2 3s. 3s full of 8s means 3 3s and 2 8s. So in a way, what we now have to do is say that there are 13 suits that I can pick from my 2 of a kind, and then there would be 12 suits left for my 3 of a kind. Does that make sense? I'm going to kind of like link these ones together. There's 13 suits that I could pick for my 2 of a kind, and then there are 12 suits left for whatever I pick of my 3 of a kind. Okay, let's find the probability, and then we'll take break time. 4 choose 2 times 4 choose 3. So that gives me my 2 of a kind and my 3 of a kind. Times by 13 choices for the first suit, 12 choices for the second suit.
I got 0.00144.
It's probably pretty small, isn't it? 52 choose 5. 0.00144?
Yeah.
As you can see, based on the probability, a full house is even less likely than a flush, which is why in the game of poker, a full house is actually the better thing to have because it's less likely. Does that make sense? Cool. Okay. Like I said, the more practice you do on these, the better you get. So today's a knowledge day. Tomorrow is going to be an application day. Practice it. And then Thursday we'll do another quiz, and I'll give you feedback. So take 5 though, and then we'll talk about mutually exclusive stuff. Sorry that I have to talk so much. Okay, so let's try some more examples. It's really more of the same, but I want to introduce a concept called mutually exclusive.
Sounds like it's hard.
No, it's just it's a twist you need to be aware of. Okay, in like the dating world, if you say that you're exclusive, what does that mean?
It means you're not cheating on each other.
Sure, it means that you're not dating somebody else, right? If I were to make a Venn diagram, here would be like one person here, and here would be, I don't know, another person right here.
They're together.
Sure. Right here, this is the section right here where there's overlap. Okay. What we want to do in some scenarios is we want to make sure that we don't count the overlap twice. Okay. That's called exclusive in math. Being exclusive in math is really not the same thing as the dating example. Okay. It's more like, let me see if I can give you, well, let's just do the example I have actually, because that's why I have the example here. So we're playing dice games. Okay. You win by either rolling doubles or when the dice sum to 7. So I'm just going to make out like We actually introduced a word the other day. It's called sample space. I'm going to write out all of the possibilities. You could go 1 and 1, 1 with 2, 1 with 3, 1 with 4, 1 with 5, 1 with 6. Bear with me. 2 with 1, 2 with 2, 2 with 3, 2 with 4, 2 with 5, 2 with 6. I'm now going to stop talking. I'll just write it out. Save my voice. Do you guys get what I'm doing though? I'm just writing out all of the possibilities. How many ways is there to roll 2 dice? 36. Why 36?
6 times.
6 on the first dice times 6 on the second dice. Here, I've got a list of every single possibility. My question is, what's the probability that you win? So, okay, well, you win by either doubles or by the dice summing to 7. So I'm just going to circle the ones in which I win. Here's a double. 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 So far, so good? And then I'm going to find all the ones where it adds up to 7. So this is a little more of a bigger list. 1 and 6 will do. 2 and 5 will do. 3 and 4 will do. 4 and 3 will do. And those ones. So how many ways can I win with doubles? 6. Or I could win with summing to 7. Actually, also 6. So 12. How many ways are there total to play the game? 36. So 12 out of 36 is my answer. Now, the illustration I want to make here is not how to solve that question, actually, but the concept of exclusivity. Okay? When you're exclusive in the dating world, it's kind of different than this. Okay? But, I don't know, maybe there is some overlap here. Is there... Actually, let's use the dating example. I think I can make it fit. If someone is not being exclusive, it means they're cheating on somebody else. Does that make sense? In this example here, that means that I would have circled something twice, where he's dating this person, and he's dating this person over here. Does that make sense? Is there a way to somehow roll 7s and also roll doubles? Does that make sense? In the same way, is it possible that the guy could be dating girl 1 and girl 2 at the same time? Have I circled the same thing twice? And the answer is no, I haven't circled anything twice. Does that make sense? That means that this is something exclusive. Okay? But there's going to be some scenarios where we have to make sure that we don't accidentally count something twice because it falls into category A, but it also falls into category B. Does that make sense? So let me try to find, well, let's just do my examples here. Okay, so mutually exclusive then is events that cannot logically happen at the same time. We need to be absolutely certain that we don't count something more than once. Okay. Here's a notation you might see. The probability of A, you guys remember what this means? This little U means? It means or. Okay. This means the probability of A or B happening means find the probability of A happening, find the probability of B happening, but then we have to subtract the probability of A and B happening. What this really means is if there's any overlap, don't count it more than once. Okay. So let me try another example. Let's say I ask you to find the probability of getting a king or an ace. And this is the work's already done on this slide for you, actually. Probability of king or an ace. Well, how many ways is there to get a king? Well, there's 4 kings in the deck out of 52. Or you can get an ace. There's 4 aces in the deck out of 52. So 4 out of 52 plus 4 out of 52. If you do the math, you get 15%. But let's say I ask you to do the probability of heads or tails. Well, you can get heads or you can get tails. Actually, that kind of covers everything. I'm going to throw in a third example. Let's find the probability of getting an ace or a 10. No, sorry, not an ace or a 10. Let's do an ace or a heart. How many aces are in the deck? Well, you'd say there's 4 aces out of 52 in the deck. How many hearts are in the deck? 13. But if you think of these as like Venn diagrams right here, here's all of the aces. Here's all the hearts. Hopefully you'd agree that in the middle here, the ace of hearts is kind of our cheating boyfriend in the example, if you like that analogy. He's dating the ace, and he's dating the heart at the same time, because he's the ace of hearts. Does that make sense? Don't count it twice. What you have to then do is subtract that ace of hearts, so you don't count it twice. That's what this notation on the previous slide says. I'll flip in a second so that you can still see this. But on the previous slide, it basically says find the probability of the first thing happening, find the probability of the second thing happening. If it's possible that you're overlapping, don't count it twice. That's all. That's what this means. Subtract the overlap. 31%? Cool. I'm not as concerned today about the math, more as the concept of mutually exclusive, because you have to keep your eyes open for it. They won't specifically tell you, hey, ding, 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 by the way, this is mutually exclusive. You'll have to really pay attention and make sure that you catch that scenario, again, so that you don't count something twice. So let's try a gambling example, if any of you happen to be poker fans. I'm sorry if you're not. I try to find different scenarios. Here is the game where currently you've got an ace and a queen, and there is a 4, a 6, an 8, and a 2 out there. Do you have anything? Not a thing. You don't have a pair. You don't have a flush, because for a flush you need 5 of a kind, and that would be 1, 2, 3, 4 of those guys right there. Phil Locke is actually doing pretty good, though. He's got 10s right now, so he at least has a pair. So what I want to do is I want to talk about the ways in which we can win. If you got an ace, would you win? Let's say yes. Because you would have aces, and he'd have 10s. So on this next diagram, sorry if it's not linked together, but I would say you can win with any ace. That's how you'd win. It is on the next slide, isn't it? Shoot, sorry, that sucks. So you could win with any ace. What else can you win with? Sure, you could win with any queen, because if there was a queen here, you'd have queens, and he'd have 10s. You'd win. Are aces and queens mutually exclusive? Yes, they are. There is no overlap. You cannot cheat by dating an ace and a queen at the same time, because there's no cards that are aces and queens. There's actually another possibility here, though. It's the flush possibility. You can win on the flush because, look, you have 1, 2, 3, 4 clubs. If the last card was a club, you'd have 5 clubs. So what that means is in this diagram right here, any of the clubs you can win with. So there's 2 overlaps because there's the queen of clubs and the ace of clubs. There is one more problem, though, by the way. This is also kind of mutually exclusive stuff. Technically, the queen of clubs is already being used. So I can't use the queen of clubs anyways because I have the queen of clubs. Does that make sense? And I have the ace of spades in my hand, so I can't win with that one. The 8, 6, and 4 of clubs are already out. The 8, 6, and 4 of clubs are already being used, so I can't win with those ones. And Phil Locke has the 10 and 10, which I guess doesn't matter because these 10s right here weren't ever going to help me win anyways. Do you guys see how I did that, though? I had to cancel the cards already in use. Yep. So I would argue that I can win on 3 aces. I can win with 3 queens. I can win with 1, 2, 3, 4, 5, 6, 7, 8, 9 clubs. So I'm going to say I can win with 3 aces, I can win with 3 queens, I can win with 9 clubs, but I have to subtract anything that's doubled up. There originally were 2 things doubled up, but I actually had to cross one of them off the list because I already own this card. The one that's doubled up, the whole point behind this lesson here is that this ace of clubs right here is counting in 2 categories. So I have to subtract the ace of clubs. That's how many ways I can win. So 3 plus 3 plus 9 minus 1 means that I win 14 times. Lost a little bit. How many cards are left in the deck? Okay, how many cards are in a deck? 52, right? So 51, 50, 49, 48, 47, 46 is actually how they do the odds. I know Phil Ock has these cards right here, but we don't actually normally know what his cards are. You know what I mean? Like in poker, you don't usually show your cards. So I would say there's only 46 cards that we don't know about. So there are 14 ways in which you can win. There are 46 remaining cards that we don't know what they are. Again, this is what poker pros do. They figure out the probability of winning. So 14 out of 46 means his probability is about 30%. I know most of you guys have showed me before, you're not big, you don't know much about poker, but did that make sense though? Or at least did the concept of mutually exclusive make sense? The fact that you can't count that ace of clubs a second time? Because you can't count it in this category and in that category. This is basically just another slide talking about the concept of overlap. So let's say I asked you for red cards or an ace. Well, you'd say the probability of getting red, there's 26 out of 52. Probability of getting ace, there's 4 out of 52. But there's red aces, so don't count the 2 red aces twice. That's all. That's pretty clear? Okay, let's just do a bunch of examples then. So, new scenario, you're playing a game. If you roll a sum greater than 8 or a multiple of 5, you win. Sum greater than 8 or multiple of 5, you win. You know what? A while ago, I made that big chart of rolling dice. I'm just going to cheat and steal it real quick right here. See if I can find a way to snag this. Copy. Paste. Okay, I'll have to erase a little bit of it first. Well, maybe just ignore the... no, I can get rid of this real quick. Bear with me. Okay, this is actually taking longer than I thought. Okay, is that going to work? Yeah. So let's figure out which of these numbers are greater than 8. Okay, well, 1 and 6, that's not going to work. This was at 2 and 5, that's not going to work. 2 and 6 is actually 8, but it had to be greater than 8, so that's out. Here's one. 3 and 6, that's 9. 4 and 6, that's 10. 5 and 6, that's 11. 6 and 6 is 12. This one should work. This one should work. That one should work. That's 10. That's 9. And that's 9. I think everything else adds up to either 8 or lower, so that doesn't work. So far, so good? Okay. And then we want things that are multiples of 5s. That's a bit confusing. What's a multiple of 5 mean? 5s, 10s, 15s, 20s. So what adds up? Let's find the things that add up to 5. 1 and 4 adds up to 5. 2 and 3 adds up to 5. 3 and 2 adds up to 5. 4 and 1 adds up to 5. So that's a multiple of 5. Also, 10 is a multiple of 5. So what adds up to 10? Well, 4 and 6. I just wrote over top of something, didn't I? 5 and 5. 6 and 4. I don't think you can actually get up to 15 on dice. So I would say then that in green, there were 7 ways that I could do something in green. There were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ways of doing something in red. But I'm going to have to subtract the 3 overlapped. So I think that means there's a grand total of 14 ways I win. Out of 36. 14 out of 36. Whatever that is, that's your answer. hopefully you guys would agree that the math is not really that different. My whole point here is just don't double count something. Because if you double count something, you're going to mess the question up. Sound good? One of the ways then that they're going to try to phrase this on the diploma is they like the Venn diagram concept. Where like here you have something occurring, here you have something occurring, in the middle is where they both happen. Does that make sense? So this right here is the probability of your washing machine breaking. This is the probability of your dryer breaking. In the middle is the probability they both break. What's sitting out here? Yeah, the probability that nothing breaks. Does that make sense? Circle 1, dryer breaks, washer breaks. Circle 2, dryer breaks. In between overlap, they both break. We'll always throw a number on the outside, which means that nothing breaks. Does that make sense? So let's see that this question makes sense here. Certain magazines done some reliability testing. They say that 22% of all washers break within 5 years. I don't have 22% written in this diagram, but I'll get to that in a second. It says that 13% of all dryers break within 5 years. And you might notice, I don't have 13% written in this diagram either, do I? And then it says 3% of the time, both of them fail. Okay, I do have 3%. Where did this 19 come from, then? Well, doesn't 19 plus 3 equal 22%? And doesn't 3 plus 10 right here equal to 13%? Does that make sense? So what we've done here is we've done a Venn diagram where just the washer breaking is 19%, just the dryer breaking is 10%, well, actually not just, both of them breaking is 3%. How the heck do I get this 68% then? Any ideas? From what though? Yeah, basically, 100% of the time, I'm going to subtract 19% where it's just the washer. I'm going to subtract 10% of the time where it's just the dryer. And I'm going to subtract 3% of the time where they both break. And wouldn't, by definition, that leave me with 68% where nothing breaks? Okay. So you might get a question that's something like this, where when I teach kids to solve it, I like to do a Venn diagram. I feel like that's the best way of illustrating it.
Wouldn't it be 10 instead of 6?
10 instead of 6. Oh, sorry, this is a 10. That's just really poor writing. You were right, though. Yeah.
Oh,
Good eye.
10.
It was just a really poorly drawn 10.
Okay,
The 1 and the 0 kind of melded together. So most of my last examples are basically their Venn diagram type examples where I'm going to give you percentages and we're going to plot them on a Venn diagram and try to figure out the probability of stuff happening that way.
So is this like a trick question or like a 68% chance that it won't break in 5 years?
Yeah, basically what that means is that there's a 68% chance that nothing will break. Right? That's what the question asks, right? Determine the probability that your appliances will not break. That's what this number out here was, the number outside of the Venn diagrams. Let's try another one here. So, according to a survey, 62% of students skipped breakfast, 24% of students skipped lunch, and 22% of students, though, eat both breakfast and lunch. What's the probability that a person skips breakfast but not lunch? Ugh. There's a lot to kind of decipher here. So I'm going to suggest draw a scenario something like this. Yeah, let's draw a Venn diagram. And I think the way I want to approach this is I'm going to approach it from the perspective of who eats breakfast and lunch. So these are the people who are going to eat breakfast, and these are the people that are going to eat lunch. So far, so good? It says that 62% of students skip breakfast. Okay. If you eat breakfast, that's this big circle right here. Does that make sense? Well, that means that 62% of people skip breakfast. So that means this spot right here and this spot right here, they have to add up to 62. Does that make sense? The people who just eat lunch and the people who eat nothing, they are people who skip breakfast. So this and this, I'm just going to say the black things here, they have to be 62%. Then it says that 24% of students skip lunch. So here, I'm going to draw this circle in. Here's the people who actually eat lunch. Where are the people who skip lunch then? Well, this section right here, they eat lunch. This section right here, they eat lunch. It means that people in this section right here and this section right here, those ones are the 24% of people who skip lunch. Does that make sense? Let me try it again then. Okay. The black circle here. The black circle of people who do eat breakfast. Well, either you eat breakfast or you don't, right? So if you eat breakfast, here's the black circle. It means if you don't eat breakfast, it means that you're in this section right here, just this little like half crescent, where here you didn't eat breakfast, and here you didn't eat breakfast. If you eat lunch, that's the red circle. So therefore, if you don't eat lunch, if you skip lunch, it means you're in this section right here where you ate breakfast but not lunch. Or you're in this section right here where you didn't eat anything.
So how do we figure it out?
Well, we still have one more number to deal with though. Okay. The last number is that 22% of students eat both breakfast and lunch. Well, that one goes right in the middle. 22% goes right here. So I actually got that section labeled. In a way, there's 4 sections to this thing here. There's the middle section where they both eat. There's this section right here where they eat breakfast. There's this section right here where they eat lunch. There's also the section here where they eat nothing. Does that work so far? We have to do a little bit of algebra now. Okay. I'm going to replace some of these things with letters. Okay. I'm going to say that this right here, can I call this guy right here X? X is the people who eat breakfast but not lunch. Y is going to be people who eat lunch but not breakfast. And then Z is going to be the people who don't eat anything at all. Because those are the 4 possibilities. Either you just eat breakfast, you just eat lunch, you eat both, or you don't eat anything. What I know is that X plus 22 plus Y plus Z, what does that have to add up to?
100.
Yeah, because that's basically everything, right? You either eat one or the other or both or nothing. Does that make sense so far? But now I'm going to go back over to here. It said to me that Y plus Z, basically, is 62. So I can write that Y plus Z is equal to 62. Does that make sense? This guy and this guy is 62%. Over here, in red, X and Z must be 24. Let me recap what we just did there. Here I said that people in this section here and in this section here, we said they must add up to 62. And I said people in this section here and this section here, they've got to add up to 24. So what I can kind of do now is solve and say, well, look, here's Y and Z right here. So how do I want to phrase this? See how this Y and Z right here? That's 62, because look, I just said up here Y and Z is 62. So what I can do is I could say X plus 22 plus 62 equals 100. What does that mean X equals? How do you get X by itself? Subtract 62. Subtract 22. What's left over? What'd you get? 16.
Has really quiet.
Okay. What does X mean? Well, this part of the circle means we're looking for people who eat breakfast but don't eat lunch.
Oh boy.
This one is the probability that a person skips breakfast but not lunch. Is that what I was looking for? Was I looking for X? No, if I'm looking for someone who skips breakfast but not lunch, I'm looking for someone who eats lunch. I'm actually looking for Y. Does that make sense? So this kind of sucks. I just solved for X right here. I now know that this X right here is actually 16%.
So then we just
Well, we're getting closer. Like, we're getting there. This is quite a puzzle. Like, this is a logic puzzle. Okay. I'm going to now go back through all of the work I did, and everywhere that I have X, I'm going to write 16. So, you guys see how right here I have an X written right there? I'm going to erase it. I'm going to write a 16. Okay, so I've used this one right here, X and Y, or sorry, Z and Y equal to 62. Now I want to use this right here as well, though. See how I've got an X and a Z right here? What was X supposed to equal? 16, right? Using this little equation right here, can I get what Z is equal to? What would Z be equal to? I'll subtract 16. I'm just going to label that on here as well. Z is now 8. By the way, this Z right here is also now 8. Well, now look, 16% right here. These are people who only eat breakfast. 22% of people who eat both. And 8% of people who eat nothing. Plus those who just eat lunch, they have to add up to 100. So how can I get this equation to get Y by itself?
54.
Yeah, take 100 minus 16 minus 22 minus 8. You got 54? That is what we were looking for. All of these little sections should add up to 100. Does that make sense? The challenging part is trying to set up a diagram and use your logic skills to try to figure out where the overlapping sections are. I'm going to need to show you a few more of these, though, hey? Like, this is not one of those things where we do it once. So I promise you, we'll do some more examples, maybe not right at 3:30, because sometimes your intention is waning. Did that make sense to anybody?
Yes. I feel like
Not able to replicate it yet, though, right?
No.
Okay, so we're not to replicating stage yet, but we are to the stage where, like, you follow? Cool, okay. What do I got left here? Okay, I've only got one example left. Let's try the last example. Like I said, I know it's 3:20, so it's not the best time of day to try something particularly challenging, but let's try another one. Here is a database where you can either have heated seats, you can have a sunroof, maybe you have neither. There's also a fourth possibility. You have both. So you could have just heated seats, no sunroof. You could have sunroof, no heated seats. You could have sunroof and heated seats, or you could have nothing. So to set this up, start with a box. And inside of it, put 2 circles. Okay. And maybe put some letters in there. This little section right here is going to be X. This little section in the middle is Y. This little section over here can be Z. And this little section over here can be W. So far, so good? Why don't we call this one heated? And we'll call this one sunroof. So there's your setup. You can just have heated seats. You can have both. You can just have a sunroof. You can have nothing. I'm going to start trying to plot some stuff here. It says that for one model, they've determined that 43% have heated seats. Where does that 43% go? Can I throw that directly on here yet? No, because heated seats would be X and Y together. So what I could do is I could write out that X plus Y, that's 43%. This whole circle right here, is heated seats. Does that make sense? Then for the next one, it says 36% have a sunroof. Well, that's this whole circle right here. So that means that y plus z, that's equal to 36%. 49% have neither. Can I plot that directly on here?
Yeah.
Which letter is that? Yeah, W is 49%. 49%, they don't have anything. Well, that gets me going. There's one more statement I can write. And this statement, by the way, you can write every single time. Heated seats plus both plus the sunroof plus neither. What does that have to add up to? 100. Okay, so now it's kind of a puzzle. You have to try to use the pieces of the puzzle to work backwards and solve for something. So right off the bat, I already know what W is, right? W is 49. So I'm just going to replace this W and say X plus Y plus Z plus 49 equals 100. And then I'm going to use like one of these little guys right here. Like say here's Y and Z. Y and Z equals 36. What do you see right here? I have a Y and Z. So Y and Z right here, I'm going to write it as a 36. So X plus 36 plus 49 equals 100. Solve for X.
It's 15.
15?
Yeah.
Okay, I'm going to now label that. That means that this X right here is 15%. So just having heated seats, no sunroof, is 15%. Well, now I can kind of work backwards a little bit and say, well, everywhere else that I had an X now, I'm now going to start making it 15. So I'm going to go and say, well, this is now a 15. This is now a 15. And this is now a 15. Cool. Now, yeah, Lisa's seen this already. Look, this last one I wrote out here, I can solve for y. So y is 43 minus 15, which is, what, 28? Cool. Well, now I can throw that up here. Y is now 28. That means that 28% of people should have both. Well, now that I throw that 28 into, say, this example right here, 28 right there, I should now be able to solve for this z sitting right here. Because I'll go 100 minus 49 minus 28 minus 15. That should give me z. I don't remember which one we were supposed to solve for. I'm just solving for all of them, then I'll look at it. What'd you get for z, though? 8? Okay. So hopefully this diagram now makes sense. 15% of people have heated only. 28% have both. 8% have only sunroof. 49 have nothing. Do all of these numbers add up to 100%? I think they do. Let's just double check here. 43 we're supposed to have heated seats. Does 15 and 28 add to 43? It does. 36 we're supposed to have sunroofs. 28 and 8 does add to 36. Now to answer the question, what did it even want? We want both leather seats and a sunroof. Well, that was the middle. That was the worst circling ever. But hopefully you'd agree, we've now solved it. It's 28% that are in the middle. Okay, I just did a second example from example 1 to example 2. Like, step up, better?
Yeah.
Cool. You just need some practice on those, I feel like. Because it's adding, subtracting. Actually, there's not even multiply or divide on that. It's really just add and subtract. So, okay, cool. I finally finished a lesson in class. Here's the plan then. Tomorrow, you need to either finish your quiz if you haven't finished your quiz. You need to finish assignment 4 and 5 if you haven't done that. There is one more assignment that we're going to do this unit, the 6th one. It's not due anytime soon, by the way, but you can start on that. Basically, the plan is tomorrow's kind of a learn day, and then Thursday we're going to try another quiz. Does that make sense? So if you haven't finished a task, do it soon so that I can help you learn, okay? Because I'd like to sit down with you and go over what you did wrong, right?
Did you mark the workbook?
No, I didn't mark workbook. Shoot, I should do that. Do I still have them? I do, don't I? Okay, I will put that on my to-do list tonight so that you guys can do some practice off those worksheets as well. Okay.
I still have assignment 4 from you.
Is it 4 the one I just handed back to you?
Yeah.
You need 5.
Okay, 5.
Okay, yeah, I can find you one. Okay, thanks guys.